Say I gave you a task, which was to describe a generic McDonald's building that you would see when you get off the side of a highway. Would it be in the middle of a parking lot, roughly square-shaped, with a drive-through and yellow accents? It could have a red roof or a sign out front with the latest deal, and of course, it would definitely have those golden arches. Now, I'm sure you've seen many McDonald's buildings before. I'm not calling you fat. We all have. This mental image is a staple in the minds of any citizen of a developed country, especially Americans. And what I just asked you to do is to recall the generalized representation of that McDonald's building from your brain. Somewhere in your head, there exists a place that has stored each of these characteristics that we just listed off and combined them into a generic image. When we hop off the highway looking for food, this generic representation is what we use to locate potential McDonald's. Now say you're walking about in Georgia, the country, Georgia, and come across this McDonald's building. First, I would say, what a beautiful building, and what a beautiful location to be taken up by a chain restaurant. But I would also know that this is an anomaly. Would it be wise to incorporate the characteristics of this building into our generalized model? All glass windows, surrounding lake, and shaped like a horseshoe crab? Probably not. We know that this is quite a unique iteration of a McDonald's, so we most likely do not encode those characteristics into our generic representation. If we had, we would get a jumbled and unrecognizable image. If we were looking for this when we got off the side of a highway, we would never eat. So this phenomenon is a classic example of overfitting to noisy data, and it has ecological implications beyond recognizing where to find the best French fries. This same principle applies to generic representations of predators, prey, and shelter. We must have stable and easily generalizable images in our head to suit most situations. We know this process to be called selective consolidation. It makes sense because we're selecting what to consolidate. This is the topic of the paper, Organizing Memories for Generalization in Complementary Learning Systems. It's by our own Professor Sun. They propose that the brain uses two complementary learning systems, one that captures specific episodes and another that extracts broad structure, and suggests that the generalization depends on filtering out atypical examples before they distort underlying representations. Now, if there's one thing I learned this semester in the NeuroAI course, it's that artificial intelligence benefits from having biological foundations. Let the brain inform AI. So, I decided to try and implement this theory into an artificial neural network. Most of this code was taken from the neural networks given to us in the homework. I'm simply not able to do any of this without that basis. This project was taken up as a challenge and not because I'm any good at Python. Now, this network is pretty simple. There's nothing fancy going on here. No convolutions, no attention. It's a straightforward multi-layer perceptron. So, how are we going to incorporate selective consolidation into this model? First, let me introduce you to the threshold. During our training period, our model takes an image like this and attempts to classify it into one of these groups. When it does this, the loss is calculated. Loss is a quantity of the difference between the model's prediction and the true label. With this one line, we throw away any training data that exceeds the threshold. This is the selective part of selective consolidation. The McDonald's in Georgia would have a large loss because it deviates from our representation. Just like we toss out an anomaly, so too do we toss out these examples that exceed the threshold. However, those of you who are familiar with training a neural network will know this won't work by itself. If we start training a model with this requirement, every training example will have a huge loss in that untrained network. It'll be thrown out. Therefore, the network will never learn. Researchers know this, but so do babies. Yes, even babies know this. That's why the dominant theory is that it takes a few years of infancy or toddlerhood until we implement selective consolidation. Therefore, we have a good baseline to work with. We incorporate this with an initial round, or epoch, of using every sample. At first, I did one entire epoch of full training, but this led to some undesirable results, because each epoch has 60,000 data points. That's a bit much. I decided to incorporate a pre-selectivity phase fraction. Basically, the fraction of data the model uses in those full training initial rounds. If we set this to 0.01, the model will train on 0.01 times 60,000, or 6,000 samples, to get that nice baseline. So let's run this thing, shall we? Does selective consolidation lead to higher accuracy on the test phase? That would be pretty crazy, right? Saying that if we reduce the amount of data, we increase accuracy. I think if we pull that off, it would be pretty awesome. What you're going to see is a graph with test accuracy on the final round on the y-axis and threshold on the x-axis. There's going to be a blue dotted line at the full trained model test accuracy. Lines for different pre-selectivity phase fraction levels will also be there. But the main thing that we're looking for is if any dot is above that blue line. That means we've made a model that uses less data and is more accurate. And that would mean selective consolidation had been implemented and worked in an artificial neural network. So here it is. And darn, we unfortunately do not improve any accuracy with our models. The closest we got was a model that used 50% of data on the first round of full training, then 2 rounds with a threshold of 4. However, what does this really mean? Let's look at the histogram of losses from our model. We can see that barely any data is above the loss of 4. And if we check the model output, we can see that a threshold of 4 means that we're using over 99% of the data. This leads us to the first finding. Selective consolidation works only with sufficiently variable data. To put it another way, there must be instances of our data that are worthy of omitting due to their sheer divergence from the norm. Our Georgian McDonald's was worthy of omitting from our generalized representation, and so were McDonald's in Sao Paulo, in Norway, Maine, Ohio, and Malaysia. Their characteristics are extraordinarily unique. In the handwriting data, there are simply not examples that deviate like this. Each sample contains valuable information that will make our model better. Any omission would be starving our model of valuable information. And another issue is that there just isn't that much headroom to improve upon this model. A normally trained model has accuracy already at 97.5%. Any increase would be minimal. So let's pivot to the slightly harder fashion data set. I'll put a histogram of the losses from one epoch trained model next to the histogram from the handwriting data set. As we can see, the data is slightly harder than the handwriting data. It has more examples that exceed thresholds, whether that be 1, 2, 3, or 4. Simply, there's more variance. So I made a model with one epoch of pre-selectivity training, followed by 2 selective epochs using this fashion data. Again, we're looking for points above that blue line. And here it is. Nice. We did it. But where and how? We get our first improved accuracy model with a pre-selectivity fraction of 0.75 and a threshold of 2. Our output told us that this model used an average of 88.7% of the data. So on those selectivity epochs, just over 10% of the data was omitted due to exceeding the noise limit. By the time the threshold is 3, all models are improving accuracy, even if just slightly. These models use just over 95% of the data when implementing selective consolidation. So around 5% of the data gets thrown out. So what does this mean? We changed data sets and ran the same model parameters and got models that improved accuracy on the baseline model. So, when we have sufficiently variable data, throwing out just over 10% of the highest noise data can improve our prediction capabilities. I don't want to overstate these effects. They were minimal. But it's not random chance that these models, such as the red line with a pre-selectivity fraction of 0.75, consistently achieved higher accuracy than that baseline model. But why this model? Why this pre-fraction? We should dive a little bit deeper into what pre-selectivity fraction is altering. This fraction is, in a sense, the amount of time or data consumed before our model starts to become selective. If we want to start being selective too soon, then we won't really be able to judge which characteristics align with our generalized model. And we won't really know which ones to exclude. If we plot accuracy against different pre-training fractions, we can see that our model needs just about 0.2 for that parameter. This is about 12,000 data points in this model. Any more data, and we're just kind of reinforming the same baseline. This makes intuitive sense, that our model that saw a little bit more data was able to make accurate judgments on loss and omissions of data. However, with sufficiently high thresholds, these fractions matter less and less. The data that would stick out like a sore thumb is noticeable to both good and great models. So, our final learning is that the pre-selective model must be adequately robust. In other words, it must be trained with enough data to establish a baseline. So, selective consolidation is reproducible in artificial neural networks with sufficiently variable data, and it depends on a couple parameters, namely threshold and pre-selectivity consolidation amount. There are a couple parameters that I didn't talk about in this video due to wanting a concise story, but also they will affect model performance. First, there's pre-selectivity epochs. I used one of these in my model, but I could have added more. Each additional pre-selectivity epoch is akin to rehearsing that full consolidation model more times before selectivity. Adding 2 or 3 more would make our model more robust. I played around with this parameter, but I wasn't able to make any interpretable findings. And selectivity epochs. I used 2 of these, but again, this is variable. The graphs for 1 and 3 selectivity epochs are on screen now. They look quite similar to the model that ended up being the main story, but without any point that improved model performance. More time could definitely be spent on why 2 seemed to be that sweet spot. There are many other baseline model parameters that can be tweaked, such as learning rate or the size of hidden layers, but this is delving further into the nuances of modeling than I wanted to go. So I think that this project is a good starting point for leveraging current cognitive theories of memory and selective consolidation into neural networks, and I think it's definitely something to keep in mind for future artificial intelligence architectures. Thank you.